Start recording. Cool. So,
Hi,
Ankit,
sir. Hi, sir.
hi.
Hey, this is Raghav. I just joined you. I'm driving and I joined you by phone. Another 10
Okay,
minutes, I'll be with PC. I'll be talking to you. All right.
okay, okay. No worries.
Yeah. Yeah.
So, because last class we did a lot of graphs and visualization and stuff, right? So, I thought we will. So, I only gave Indian liver patients last time, but I thought we will do some again a little bit of data visualization with video game sales data. We'll start that. Wouldn't expect. I mean, I'll walk you through the code which I have, and I will revise some of the basic things this thing, but I don't want you to code everything in video game visualization for now, because we are going to learn a new machine learning algorithm today. So I would prefer you guys spend most of your coding time on that algorithm. This is the first time I will show you like what packages we use, and how do we actually uh, you know uh, do the data visualization, everything in that algorithm. It's I think the most simplest algorithm which is out there, so we can start with that. But before that, just 1 second, there's one person pinging me on the phone. So before we go there, so all of you downloaded the video game sales data. So I have like 3 data sets for today's class. You should, I sent a mail, please download them. For now, I actually sent 3 data sets. One is the accelerometer data, other is a 3 class cluster example, and video game sales. Just to start with I mean, just to revise the last class, what we did. Let me just pull up that presentation. So as I was saying, actually what I had planned today was to introduce R and programming in R, but I kind of feel like just now we've started learning Python, right? So we're going to stick with Python for the next 2-3 classes, and then we will do R and linear regression and stuff like that. So last class we've actually seen pandas data structure, like how we can basically import data sets into pandas. Two main things which we use is series and data frames. Series is mainly used when you have like one-dimensional vector, like when all the data points give you the same are belong to the same category, like when all the data points belong to the price of a stock, or they belong to maybe the weather data and stuff. So when you have a one-dimensional array or a list of the same type, we use series. We can use series when I'll talk about using the series when we do linear regression and stuff. But for most of the cases, we use data frames. Pandas data frame is the way we actually read all the objects into, or all the columns and all the observations into one particular data frame. And I sent an example yesterday as to how you actually create a matrix from that particular uh, data frame. So one thing which people were asking last time was how do we actually find, because we did a lot about the rank of the matrix and linearly independent and dependent columns, right? And then one way I said, like before we do principal component analysis, one way I said to make sure that each feature is linearly independent by calculating the rank of the matrix. And the way we calculate the rank from the matrix, I think is, um, I think it's taking some time to load. But the way we calculate the rank of a matrix is there is a function called as underscore matrix. So you actually call that on the data frame. So you use the data frame and say dot as matrix, and you give in whichever columns you want to provide. So in this case, we gave the column because the 11th column was actually data it was the data type, right? So we actually used the data frames columns from 0 to 10. And then from that 0 to 10, we actually created a matrix. And then from that matrix, you can actually find out the matrix rank by calling the NumPy package called linear algebra dot matrix underscore rank of that particular matrix. And you will see that you can take like 10 features from that matrix and you will see that the rank of the matrix is actually 10. So that is proof for us, initially a validation to show that all the features which we have in the data set is actually relevant to us. So having done like pandas and stuff, what we did is we went into visualizations. So two main packages in visualizations which we saw were matplotlib and Seaborn. So so we have seen like different kinds of visualization, like histogram plots, kernel plots, scatter plots, bar plots, box plots, violin plots, etc. But there are like a lot of other plots in Python. So these are just some of the plots. So today, the next case study which we have is the video game sales. I'll show you how to do stacked plots and basically rainbow plots and stuff. So that will help us add to the visualization which we have been doing. So we'll start with so Seaborn, yeah, Seaborn and Matplotlib are the two main things. Seaborn actually provides us the box plot and violent plots, but there are other plots which we will see today. So before that, right, like what is the first thing which we need to do when I give you a data set? Like I gave you the video game sales data set, right? What is the first thing we need to answer about that data set before we start anything, before data visualization or before writing machine learning algorithms on that data set? So what is the first thing you do with that data set? So we just,
You clean the data.
yeah, so we firstly clean the data and analyze the data. So so first step even we did with Indian liver patient was analyze the data. So basically even in video game sales, so like if you have downloaded the data, let's just take a quick look at what is present in the video game sales data. So this is the data coming from different publishers. Like we have like name of the game, which year it was released, which platform it was released. So all of you can just take a look and see like what are all different fields in that data set. So it shows you who the publisher is, like what is the sales of that particular data, what I mean, North American sales, EU sales, Japan sales, and other sales. So this actually gives you a metric to see like so. And we also have the genre uh, of the of the game. Like, is it a racing game? Is it a first person FPS, first person shooter game? Is it an action game? And stuff. So basically, with all this data, so first thing which we would want to actually compare is so how do like so this is a question, right? Like now you are given this data, so you need to answer a lot of questions. Like maybe one question is which years were gaming. Like we have the if you see the data has been like Mario Brothers has released Mario in 1985, and we have the data from 1985 to 2018, so we have like solid like 23 years worth of data. So with given this data, like what all can we answer? Like can we say that is the video games craze increasing or decreasing, or which years was it maximum, and in those years which are the games which were more popular? Like if you are in the sales industry, right, you need to answer a lot of questions like this to come up with strategies, like even to recommend strategies to your management and stuff. We actually have to answer a lot of questions as to like where is the trend of the industry going towards, what are the games which people prefer versus what are the like which even which consoles. Let's say you're working for like EA Sports and stuff, right? So you'll actually need to do this analysis as to do you write the game for Nintendo, do you write the game for Wii, do you write the game for like Xbox and stuff. So for these kinds of visualizations, later on we will see how we will use this data for doing machine learning. But the first thing which we have started as of last week is data visualization. But before we go into data visualization, step number one is always clean the data, because any algorithms or any plot, when they see this not a number or missing data, they just won't work. So the first step is to find out how many of the values are missing or how many of the values are nans, and then we fill those values with either zeros. And the other thing which we do is convert, basically, let's say we have three publishers here, and let's say we are writing an algorithm which actually takes this as a feature. Firstly, it is text, right? So machine learning algorithms, like, because everything else is in number format, you have to basically convert this into number format. The way we do that is pandas has this thing called dot categorical function, which will take in, it will find out, oh, what are the total number of categories, and start assigning it uh, a number value. So all Nintendos will become 0, Microsoft game will become 1, other things will become 2, and stuff like that. And even so is the genre, so is basically everything which is actually having text, you can make it into categorical data. So let me quickly show you the first step which we did here is, so firstly, I actually, the thing I follow is, basically I look at, uh, like, I just first print out the 10 records. Like, you can either open Excel and do it, or you can just write a program to see. I print out the first 10 records of the data to see what does the data contain. And then I get the shape of it, like to see how many number of rows, how many records are there in the data set. Then I get the columns of the data set. So what will give you that is the data frame dot shape. So if you do data frame dot shape, the 0 will give you the number of rows, and 1 will give you the number of columns. So you first answer that number of records in that, number of columns in that, what are the column names of that particular thing, what are the types. We did this last time to see all the columns which are object types, and we converted them into like numerical types, right? So, and then we can do like more analysis, like what are the number of unique platforms. Maybe I think just for like, you don't need to do everything, but just uh, load this data and then print out the unique platforms. Like, this is the thing. So basically, there is a dot unique function which is new to this particular thing. You actually take in the columns, and then use dot unique. It will print out the number of columns which are unique. So why don't we quickly load this data set? If you are this thing, so load the data set on the CSV. Like, read the CSV file, and then there is one additional thing here. You actually have to open it. uh, you need to use an encoding here. So what is this encoding? So basically, in general, right, like, let me just show you a small, so generally whenever you're typing anything on, like, say, notepad, so write A B C D, capital A B C D, so all these are ASCII characters. So ASCII characters, I think, are like 0 to 256. So all these things are called, they all come under UTF-8 encoding. So UTF-8. So what that means is basically, so for 0 to 250, so every character here, you assign a number from 0 to 256. So that's basically ASCII encoding. But let's say you have Japanese characters, right? I don't have Japanese keyboard for me to type. But if you look at this data here, there'll be some names which actually have these Japanese characters in these columns. So when you try to read them, it won't basically read all those values. The reason being because they are out, and by default, when you say pandas read CSV, it will try to read it in UTF-8 format. But so if you have, like, if you're analyzing sales data from other countries, like you have Singapore, Japan, China, and stuff, you need to change the encoding. So this UTF-8, we can only read up to like 0 to 250, 0 to 55 actually. It can only read 255 different types of characters, in which ABCD, small ABCD comprise of 26, capital ABCD comprise of other 26, and then you have the special characters like exclamation, at the rate, asterisk. All those come in this 256. But if you're actually including like Chinese or Japanese characters, it can't be because 0 to 255 is already taken. So you actually go for different encodings. So there are different kinds of encodings, and especially to read this particular encoding, this particular data, you need to give an additional encoding. We use Latin L encoding. So the Latin L encoding will expand the encoding from UTF-8 and will provide more characters to it. So in case if you have any characters which are not falling under the standard ASCII format, you can actually read them from this thing. So if so, as first step, so you read that into the CSV. And we did this exercise for Indian liver patients. If you remember, we actually printed out the number of columns, we printed out the column values, we printed out D types. But this was something which we didn't do. Like you can take a particular column and say dot unique. It will tell you what are all the unique platforms which are there. And then there are like a lot of things like print starting year, which is the maximum of that particular column, print ending year, and what are the different kinds of genres and stuff like that. So if you have if you are programming right now, just try to print out the unique. The rest of them we have anyway done for Indian liver patients. So once I give you this particular data set as assignment, you can basically run these other steps. So let me just so it will start. So this is the first basic analysis step. So you can see it will print out all the data which we need. So what are the different platforms we are using? Nintendo, PS1, PS2, 360. Like there are different other platforms which, because we started from, sorry, it's not 85. We started from 1980 to 2020. So we have like good 40 years worth of data. I mean, 2020 is not yet there, but that is used for prediction. But so, and then we have different genres. We have sports, platform racing, blah, 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 blah. And then we have different kinds of genres. But then we do the standard exercise of how many records on this have nan values, which is not a number. And then we will proceed from them. So first step is analyze the data. Second step, what we do with any given data set is clean the data. So when you're cleaning the data, what we do is we convert everything into categorical values. So the drop NA. So there are two things. If you remember last class, we did fill NA. Fill NA means that you're going to take a nan value and convert it into zero or whatever number you provide there. But then there is another function called drop NA. What drop NA does is basically it drops all the values which are missing or which are nans. So then comes the second step. Again, you mind you that every time you actually load this particular data set, you have to load it in Latin L encoding, or else it won't read all the formats and stuff. So the first thing I do is I try to find out which, if there are any ones null. If they are null, I want to print out the number of ones which are null. And then the second step I do is I actually drop everything which actually is not applicable. And then basically then we do the usual task of like creating categories from the object data. So we actually get all the object data and then we create categories. So there is some other thing which I've actually done here is, because a lot of times people don't know which company is PS3, PS4 and everything coming from. So what I did is anything which is having PS3, PS4, PS4, this thing I actually renamed it to Sony PlayStation, and everything else which Nintendo has, I renamed it to Nintendo as the company. And Xbox has Xbox 360, Xbox One. I renamed it to Microsoft Xbox. So that way, actually, so now and then after doing all that, I store it as video game sales dot cleansed. So this is the basic exercise with it. So we already went through that for Indian liver patients. So I'm not going to like stress only on that. So yeah. So but just to give you an idea as to what are the steps which we need to do on a regular basis is basically the fact that we analyze the data, we clean the data first, and then comes visualization. And after visualization comes the fact that we are after visualizations we come and see which machine learning algorithms are applicable. But let's see how we can answer some of the questions in this. So in visualization, I'll show you two additional plots. They are both a part of Seaborn. So first plot is the factor plot. So what factor plot does is, let me just show you how it works. So I take in the data, and then so the factor plot will tell you, it'll take the year data, and then it'll basically plot it as as it increases. So you see like this, you see, I mean, so this is basically a visual representation of the factor plot. So what that does is it takes in all the years, and then it factors in how much is the sales per year. And it has this cool thing where it starts from like completely faded. You can give any color you want, faded purple, to like as it approaches to the year end, you have like the solid purple and stuff like that. So you can, let me show you this thing. So looking at this graph, right, this will tell you, so this is a factor plot. So in factor plot, it takes in the number of years, and it takes in two columns basically, year column and the number of sales column. So looking at this plot, right, what all can we answer? So this is, like a data intelligence question. So I give you this plot. So I'm telling you that this plot is basically the year of release versus the number of console games sold. So what can you say about like, and is it giving any intuitive knowledge when you look at this graph?
Like the video game sales was increasing from like 2004 to 2008-ish, and then after that it's a constant decline.
Yes, that's absolutely true. So basically, the video game sales were at the peak in 2008. So up to 2008, like people, the reason being, we actually, so you can see like how, how that ties to the next set of graphs which we have. But the first category which we see is, it was actually increasing till 2008, and after 2008, it slowly started decreasing. So then we look into the data to see why is it decreasing. Because after 2008 was when, anything interesting about 2008, if you, all the people who were working would probably remember 2008 now.
The recession.
Exactly. So there was this recession which hit in the year 2008, and a lot of people, lost jobs and this thing. So then people started spending less on video games, because video games is an, it's a luxury, right? Like, I mean, when you actually have everything else, that's when you spend more on video games. And a lot of these companies which actually were there up to the year 2008 went bankrupt and shut down. So the total number of games, so the major companies games are still there, but you can see that as after 2008 there has been sharp decline. So at least this graph tells you like the nature of how, how the video game sales data behaved. So this is basically called a factor plot. So you can see, this is the next plot. I'll show you. Like, let me just show. So the thing is, like, we can do a lot of plots and stuff, but I want to start with like machine learning, because we have a lot of algorithms which we want to cover later. But anyway, don't worry, I'll give you the whole code. So it's called SNS.factor plot. You need to provide X, which is the year of X is the X-axis, and then the data is the sales data of that particular data frame, and what kind of it is a count. And I used a blue, they said this is the palette is that violet color which we had, and then you have to order it with the number of years. So this is the format in which we actually use the factor plot to plot it. But that's still, and then you can add in labels to it. We saw how we can add labels last time, right? X label, Y label, title. And then ultimately what we do is basically we say, show that particular, plot. So it creates a palette, and you actually do a factor plot, and then ultimately you show. So the next graph which I'm going to show is basically, it's called the stacked plot. It's called like dot unstack dot plot. So what stack plot does is it stacks one thing over the other. So if you see here, so you see Xbox, Nintendo, PC games, Sega, Sony PlayStation. All these are different colors, but according to the year, I'm stacking them over one over the other. So you can see the white part here, Xbox, number of the number of sales for Xbox versus Nintendo versus PlayStation, and uh, so so this will answer a few questions. So basically, until 2001, Microsoft never released its Xbox, or they had like very few titles. But basically, PlayStation, Sony always was into gaming. So you can see that their chunk is like really high. But then afterwards, in I mean this is very like intuitive because Nintendo came up with this Wii. I don't know if you guys remember. It was a huge sensation back in 2008, say 2007, 2008 time frame. Wii basically it had this joystick handle, and you can just play tennis. You can play different games with the Nintendo Wii. How many of you actually played Wii? Anyone maybe with kids or like yeah? What about
Played
Meher?
V?
Yeah, Nintendo Wii.
Oh yeah, I played it.
Yeah, so that was a huge craze. So as soon as Wii became a success, a lot of gamers started making more games for Wii. You can see that their chunk increased quite a bit because I think they launched in 2006. So you see this Nintendo's color is the color is slightly different. It's not pure white; it's grayish. So you see that their games actually increased, uh, actually quite chunk. 2009, what happened? Anyone remember 2009, 2010? Basically, year 2010, something happened. So 2010, Microsoft came with its competitor called Kinect. I don't know if you guys know or you play with Xbox, but Kinect was released in 2010, and Kinect was a big success, and it ate most of the Nintendo Wii's market. You can see that their market share, basically the number of sales for Nintendo Wii for 2009 to 2010 has decreased significantly. But PlayStation kind of remained constant because PlayStation was always providing the same titles and stuff. But Microsoft actually, Microsoft Xbox actually released this thing called Connect, and 2010 that was a big success. Like I think they sold like 8 million units in like November December time frame. So uh, 1 second. Okay, so basically yeah, so that was one of the things which happened. So anyway, like this is one of the stack graph which can explain, or whenever you look at data, and if you are a data scientist, you need to think data, speak data, and you need to like all these plots will come in handy to answer your questions because everyone can get the data, right? Like nowadays we have like big data systems and a lot of people can cook the data, but the real value add is the person which can kind of make sense with the data and can solve problems looking at the data. So that's why there is such a big demand for like data scientists these days, is because now that we have so much data available from like smartphones, we have data available from shopping history, we have data available from a lot of things. Like when we so in fact I didn't introduce all the case studies. We have like 10 to 12 case studies which we'll do, in which we'll see we have data from like there is one thing in linear regression. It's a biking data. So in New York, depending on the weather, this company wanted to predict how many bikes should they put in their shop, so that if the weather is really bad, then they'll put less number of bikes. The weather is really good, then they put more number of bikes. So they want to because keeping, if people want to bike, right, and you can't, basically it's not something which can be assembled immediately. So they actually wrote this predictive algorithm where you can say how many bikes should I stack for tomorrow depending on the data from the past. So we'll do that later when we do logistic regression. But you see that there is a basic sense in how so these are called stacked plots. We can actually use stacked plots to answer comparative analysis of the data. So if you want to compare like different kinds of the sales data and stuff. So this is one of the plots which Python, this is all Seaborn again, so that provides. And then there is this other really cool plot. Let me just show you that plot. it's also called stack plot, but then the color map is rainbow. So when you give the color map as a rainbow, it will provide this thing, really cool plot, which is like a rainbow. It uses all the WebGR colors and it will provide it. In this, I passed in other column, basically the genre, right? So you can see that, so each color represents a genre of the data. So like, for example, strategy-based games are like red. Then we have racing games, which are like, like green, and then action games, adventure games, and stuff. So this will give you an answer as to like what games are becoming more and more popular. So as you can see, there's a huge chunk of action-based games have been like being more popular, and then come strategy-based games, which are this thing, which have been more popular. And you can see that this thing, basically, uh, fighting games, especially, they seem to be on a decline. Uh, one-on-one fighting and stuff. So people don't seem to be like buying those things anyway. But and then there are role-playing games where you have where you actually change different roles and stuff like that. So that is another kind of genre of games. But this will overall give you an idea. So let's say if you're a data scientist for a gaming company, right? So it'll give you more inference into like what genres. Why would that company hire you in the first place? Because they'll ask you, hey, looking at this data, can you recommend us what kind of games should we make? What kind of basically, what is the trend right now? Is the trend people are playing strategy based games more? Are people playing sports based games? Or are people playing action based games? So a lot of people, then you can look at this data and give them this input as to like what are the different kinds. And then these are really good for presentations too. Like I know there's Power BI is another thing which I know people use quite a bit for presentations for this thing. But as a data scientist, it's also very good for you to understand, because this is all you. The reason is you can make this all programmatically, and you can actually play around with the data. Once you load it into a data frame, you can analyze different uh, different columns, different like aspects of it and stuff like that. So this is basically, I think, I just wanted to cover the first half an hour. I'll give you all this programs and stuff, so please go through them. So they're pretty standard graphs, and how we pass things and things like that. Just one thing is, when you change the color map to like rainbow, you can experiment with other color maps too if you like to. If you have any more questions which you want to answer, you can actually answer them based on the visualization. But this pretty much uh, concludes our data visualization for both. So we did two case studies. One is Indian liver patients. The other one, which we saw today, is video game sales. So these, and then both of them come from Seaborn and Matplotlib. So using these two data visualization tools, we can actually do some really cool visualizations and stuff like that. So any questions so far on visualizations? Anything? Because this, I think, this gives you a good introduction into like scatter plots. We did box plots and violin plots last time, and every plot answers a different aspect of the data. Because I think one thing which we did was we compared the snowfall in Snoqualmie and Whistler to see which one is having a higher snowfall rate, which one is actually better to go skiing like over the week and stuff like that. So basically, instead of looking at the data, these graphs will help you understand how the distribution of the data is and what are the trends in the data and stuff. So if there are no more questions on like data visualization, I think we will do one. So we'll get into machine learning today. So we will first. I'll start with one of the most simplest algorithms out there. But again, at this point, any questions on data visualization?
Sai, there are like, uh, I mean, there must be something available for the uh, visualization part, right? In terms of making it more colorful, or making it 3D or
Yeah, so there are these functions which are there, and like the color map will tell you like what kind of thing. Mainly, color map will make the different color maps you choose, the different colors you get them. So like in this case, when we did stacked, so when you do stacked equals true, this is what will stack both of them together. And so each of these things actually have a meaning. Like the stack plot, if I actually do it like an area, so when you see the last plot here, it was the area actually tells you what. Let me run it again. So this one is a simple bar plot, right? Like which we did, it's called factor plot. And the next one was a simple stacked plot. So we actually just did stacked. But if I want to make it like an area plot, so this is the next one is area and rainbow. So all this, the area will denote the, the nature of the sales, and then different colors will denote uh, and different colors will denote like different genres and stuff. So if you play around with this unstack.plot function, where you actually have different color maps, different kinds of plot, you can either plot it as an area or you can plot it as a bar. The
so for
second,
example, in a pie chart, right? If I'm trying to do a pie chart,
yeah.
I just want to show one particular pie away from 3/4 of the pie, like a 3D. So
So this will, I mean, one particular pie away from this thing. I'm not sure if there is a way, but you can actually use pie charts, basic pie charts in Seaborn also. So there's a pie chart library in which you can actually just given the data and it'll draw a pie chart. But these are slightly more advanced plots, where because pie charts and everything are available in most like Power BI and stuff. So they're like standard plots which they only tell you like what percentage belongs to what, right? But these things will answer a little bit more when you want to do comparisons, or when you want to gives a better visualization according to, like, especially scatter plots, right? So last time we saw that when we are looking at two columns in Indian liver patients. So like these answer questions based on like how machine learning algorithms uh, need the visualization to be. So yes, last time we saw that these scatter plots are helpful in understanding how data segregation between two columns actually behaves. So these are more specific towards like data centric. I mean, the reason we are doing this is, yes, I said that, yeah, you can make management decisions and stuff, but the reason for these visualizations is because then we will first look at the data and then see what kinds of machine learning algorithms we have to use. So in this case, we know that this data can be separated by two lines, so it's a linearly separable data. So we will use probably like linear regression or something of that sort to to differentiate between them. But if the data is all cluttered, then we use more complex machine learning algorithms like support vector machines and stuff. Anyway, when we actually get into those machine learning algorithms, you will then realize like the importance of like what this data visualization is telling us and stuff. So these plots especially are for data science, or like to understand like what kinds of machine learning algorithms should we use in the future. So if we are done with like the plotting as such, so I want to read. So until now we have learned Python. We have learned how we can read the data, how we can analyze the data, how we can clean the data, how we can visualize the data. But the next step, or the main fundamental thing after the feature engineering is done, is machine learning algorithms, right? So for that, so there are 3 or 4 main categories of algorithms. Let me just so I actually divide machine learning into like, so there are firstly there's supervised learning. Sorry, there's supervised learning, and then there is unsupervised learning. So these are two categories of the way the machine learns. So I think I've actually briefly discussed in the past what supervised learning is and what unsupervised learning is. Can anyone tell me the difference between both of them?
Supervised learning is when we know the qualities of the data, like we we know what it the feature engineering. We know the features and we know what the data belongs to,
So
and
when you
it comes from
have labels,
tables here.
That means when you actually have the features, everything needs features, right? When you have features, and then for every feature you have the label of that feature, like this particular feature, is it belonging to, like if you take Indian liver patients for example, we have the feature like age, we have the bilirubin count, we have the alkaline phosphate count, but then at the end it tells you whether this person has the disease or doesn't have the disease. So whenever we have labels, or when we teach the machine along with the labels, it's called supervised learning. Most of like around 80% of algorithms are supervised learning algorithms, because we need to teach the machine, like when you're training the machine especially, it's better to know what you're training with. I would say like 20% of the cases we would probably use unsupervised learning. It's only because we don't have labels. If you have labels, because the accuracy of supervised learning is much more, right? Because it's like teaching a kid a difference. I mean, I know I quote this example quite often, but teaching a kid the difference between an apple and an orange. So when you show the kid an image of an apple, you have to tell him this is apple. Then and then show him another image and show apple, 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 right? Uh, there are some things which, like the machine tries to figure out automatically looking at the data. So that is unsupervised learning. But generally, unsupervised learning, some cases is uh, accurate, but anything which you can do with unsupervised learning, you can do with supervised learning if you know the labels. So we will first start with unsupervised learning today, because this we will do an algorithm in unsupervised learning, and you will understand once I actually plot the data. You will understand to see, hey, without the labels, how is the machine learning uh, the different classes of the data? So these are two learning mechanisms, right? Supervised learning and unsupervised learning are two learning mechanisms. But then, so these are learning mechanisms for machine learning. Learning mechanisms. But what is it learning? So this is a learning mechanism. What is it learning? What is the machine learning about? So this is the subcategory. So both these are two learning mechanisms, but then these learning mechanisms solve three main classes of problems. So one is the classification problem. Classification. What is classification? Classification is when you ask the machine. So you already have like training data set, right? You train the machine with the training data set. So when you ask the trained machine what class is the problem, like what class is this particular observation, like if we take the Indian liver patients again example. So I have an observation and then I have a class. I say one if the person doesn't have a disease, and then two if the person has a disease, right? So there are two classes to the problem. So classification problem is the set of problems where you actually given a new data and tell me, like, now this is the training data, so now I have test data. In test data I don't know the label, so I given the new observation and tell, hey machine, you have learned what these like what kind of data provides what kind of data is having disease and what kind of data is not having disease. For this new data set, please classify the problem. Please classify it as having the disease or not having the disease. It need not be only two classes. Sometimes, like for example, let's say we are taking the fruit classification problem, right? So we have multiple classes in that. Let's say we have apples, we have oranges, we have mangoes, we have like grapes. So this is a four class classification problem. So this is one class, this is one class, this is one class. So these are classification problems. So supervised learning and unsupervised learning are the way the machine learns. So they don't get confused between the type of problem and the way we learn the problem. So these are types. So we can do classification both using supervised and unsupervised, because supervised and unsupervised are the main distinction is basically having labels and not having labels. But the type of problem we are trying to solve is basically these are the types of them. So one of the main problems is classification. In classification, you basically train the machine to tell you which class the data belongs. Again, I think we did this last class also. So uh, when we saw the data for the people who had the disease and who did not have the disease, what what is meant by the machine is learning. All the machine decides or machine learns is the boundary. So this is a mathematical equation which the machine learns from the data. So machine learns the boundary. So decision boundary. The decision boundary being, like, if you have the data which is like this, the machine somehow comes up with a mathematical equation saying that, hey, this is the decision boundary that I learned from this training data, and it remembers this particular boundary. That's what we say is a learned machine learns this particular thing is basically it learns the decision boundary. And once it learns this decision boundary, when you have test data, it'll only plot the test data in on the graph and say if it is lying on this side of the boundary, then it is someone who does not have the disease. If it lies on this side of the boundary, it says that it is having, that person has a disease. So we did this in the last class. Anyone has questions on this? What exactly do we mean by machine is learning? Machine is learning the decision boundary. The decision boundary is the boundary which separates the two classes into two sides of the decision boundary. On one side, you have all the points which are having disease. On the other side, we have the points which are not having the disease. Is this thing clear so far? Like what classification problem is? Any questions until now? I'm assuming everyone understood, right? You can tell me a yes or a no. It'll be helpful.
Yeah, no questions.
Okay. So this is a classification problem. Then the other set of problems, they are called prediction problems. What prediction problems do is you give it some data, some training data, like this is how the nature of the thing behaves. And then you tell me, hey, predict what will happen later on. So this is a time, right? So you're telling that until this time, the nature of the data is like this. And then tell me how the future behaves. So that is the second class of problems. It's called prediction problems. This one we'll do two algorithms called linear regression and logistic regression. So they are the problems, they are the algorithms which actually explain this set. So first is classification. Classification will classify between data. Second kind of problem is actually, you know what, I need to draw this. So first problem is classification. So classification problem actually classifies the data between different classes. Second kind of problem is the prediction problem. So prediction is basically you give the machine, so prediction is always with respect to time, right? So you tell the machine that, hey, this is how the data is so far. From now on, given some particular time or given, or you can even put this as X and Y, right? So X axis and Y axis. So can you predict what the value will be for a particular X? So that becomes the prediction problem. So then there's a third category of problems, which are basically called the one which basically we dealt with last time. It's basically called it's basically based on the reward based this thing. So we won't deal much with this kind of problems. basically these are mainly used in robotics and stuff like that. So what in this kind of problems, you basically make the machine choose, uh, decide based on like which path it wants to take, where the reward is maximized. So I'm forgetting the actual class of problems it has. It was there in the first slide which we did. So when we did classification prediction, it is, what is that class of problems based on? Anyone remembers that when I told like this is basically used in robotics and stuff? The class of problems which are based on reward based, where you actually have a maze and you have a reward for every time the robot tries to move left or right and stuff like that. So anyways, this kind of problem we won't be learning much, but most of the cases we'll be learning these two problems. So, so now, so these are the types of problems. So again, but then there are two types of learnings, right? There's supervised learning and then there's unsupervised learning. So does anyone have an idea as to how unsupervised learning would actually work? Like there are no labels, right? So how will the machine, so let's say we are doing classification problem in unsupervised learning. So I need to classify between two classes, but I don't have labels. So how will the machine learn the decision boundary or anything in this case? Any guesses?
Does it group it into similar items or something?
Exactly. So grouping is the first way. So in this case, before I do that, right, like we've discussed this. Let's say first thing, when you have data, you have features, right? You have features. Like you have feature 1, feature 2, feature 3, feature 4. We take Indian liver patients, we had like their age, their alkaline phosphate count, their bilirubin count, like different blood sample features. So we did this, right? So everything has certain value like 0.8, 0.7, 0.22. So let's say we have 5 features. So if I plot this particular observation in a 5-dimensional plane, so there are 5 dimensions. It's really difficult to imagine 5 dimensions. So what does this feature or this observation become in this 5-dimensional plane? So this is observation 1 for one patient. So we have let's say this is 5 dimensions somehow. Just imagine a 5-dimensional plane. So if I plot like, okay, first axis will tell me feature 1, right? Second axis is feature 2. Third axis is feature 3. And then fourth axis is feature 4. So when I plot this particular observation in this 5-dimensional plane, how will it look like? Okay, let me take something more simple. Let's say we have only 2 features. We have total bilirubin, like bilirubin, and alkaline phosphate count. So they are just 2 features. It has 0.8, 0.99. So let's say I want to plot these 2 features in a 2-dimensional plane. In 2-dimensional plane, this would be the bilirubin count. This is the alkaline phosphate count. In 2 dimension, how does this observation look like?
It's a point.
It's a point, right? So if I have 2 features and I plot them in 2-dimensional plane, it's a point. So let's say I add one more feature. Let's say I add age, and I add one more axis here. Age is another axis. Now what will this thing look like?
It's a point in space, right?
It's a point in 3-dimensional space.
Right?
Because there are 3 dimensions and each one has a value, right? So this has 0.8, this is point something, this is, so each observation becomes a point. So now let's say I have five features and I have 5-dimensional space. in the 5-dimensional space, even this observation will map to one point. Is everyone clear with that? Because each of the dimension is basically giving you one of this value. So that's why, I mean, maybe 5-dimensional plane is difficult to imagine, but then that's why I did with 2 dimensions, then I went to 3 dimensions. Then so in a 5-dimensional plane, so there are 5 axes. So there is one, I don't know how they will be oriented, but there are like 5 axes somehow. I mean, just imagine there are 5 axes. So each of the observation in this 5-dimensional plane is again going to be a point. What is the value of this particular point? It is basically whatever feature 1, feature 2, feature 3, feature 4, like in that dimensions, everything, it'll move inside or outside and stuff like that. So it becomes a point. Is everyone clear with why so if I make a generic statement, if there are n features and I have an n-dimensional plane, when I plot each observation in this n-dimensional plane, it will become a point. Is this clear, or does anyone have any questions? Why would it be an point? All I'm doing is I have n columns, and I'm somehow having the imaginary n-dimensional plane where each dimension is like a line. Like in this case, we had alkaline phosphate and bilirubin, right? So these are two. It's easy to imagine in 2 dimension because they're both like x-axis and y-axis, and we have 2 points. You have 2 values, so this will become a point. Some other case you have like 0.7 and 1.2, it will become another point. Each observation becomes a point. So when you have like a lot of features, like n features, you have to imagine an n-dimensional plane. Then each of this observation becomes a point. Is this thing clear, or does anyone have any question? Because this is the fundamental thing which you need to like understand, is how the feature space looks like. So when you have like, so all these, like when I'm looking at even video game sales data, right? All these are, each individual one is a feature. So this one, each of them is a feature. So if I actually take a space where you have 1, 2, 3, 4, 5, 6, 7, 8, whatever, like 10, these are 10 features, and if I have a 10-dimensional space, each observation here, like this observation, you can map it into a point on that particular space. Is that clear? Why it will become a point?
Yeah.
Because each of them can be represented by like similar to like 2-dimensional geometry. Each of them can be represented by the set of n values. There are n dimensions, and then each point, maybe I will just drawing skills on that, and each of them will become one point, and this point's value is nothing but whatever this feature is. There's another observation, that would be another point. Another observation, that would be another point. So all these things are points in that n-dimensional feature space. It's clear up to this, right? So let's say when I plot all these observations into this feature space, right? So I have, each observation is a row, right? This is video game sales, but then we have like the other thing is basically like Indian liver patients and stuff. So all of them become like points in this n-dimensional space. Now let's say, let me just clear out. I'll just draw 3 dimensions for now. So I have 3-dimensional space. All these are 90-degree angles with each other. So now now let's say for Indian liver patients, right? I take observation 1, it belongs here. Observation 2, it belongs here. Observation 3 is here. Observation 4 is here. Observation 5 is here. And then there are some observations which are here like this. So I just give you this plot, right? Each of them is an observation. Each of them belongs to one patient. So I just give you this plot. So when I give you this particular plot, can you actually, I don't tell you which one has I'm not telling you which one has disease and which one doesn't have a disease. But looking at this plot, can you tell something?
You can probably group it into two.
Exactly, right? So you can see that these things are somehow, this is one group, this is another group. Though I don't tell you which point has the label or not. Like, let's say if this one has disease and this one doesn't have disease, I won't tell you that. But I'll tell you that this is the Indian liver patients data. And this is the data of people who have the disease and who don't have the disease. I won't tell you which individual point has the disease, but when you plot them in this n-dimensional space or three-dimensional space, you look at the nature of the observations, and you see that there are two clusters in that observation. So there's one cluster like this, the other cluster is like this. So somehow intuitively you will come to a conclusion that, hey, if these are two clusters, then maybe this cluster does not have no disease, and maybe this cluster is a disease. So this is what unsupervised machine learning does. One algorithm, one of the most famous algorithms in case of unsupervised learning is called K-means algorithm. So we're going to talk about K-means algorithm today. So K-means algorithm tells where K represents the number of classes. K-means algorithm is so in this case, we just saw that there are two clusters in this space. We don't know which observation belongs to what category. But for some reason, when you plot it in the space, you see that there are two clusters. There's one cluster here and there's another cluster here. So intuitively, we actually can make sense that, hey, if the data has two clusters, then maybe that one group belongs to one class and another group belongs to another class. So that's why this clustering algorithm is really popular when the data you choose is really good, and then somehow the data can be segregated into different groups. Is that clear?
Yes, sir.
Okay. So what does K-means algorithm do? K-means algorithm only tells the machine that, hey, I have this data, and I will tell you, all I know is I don't know the labels. I don't know how many, I don't know what each observation does. Each observation can have the disease or cannot have the disease. But I'll tell you that there are two classes in that particular thing. First class is have disease. Second class is does not have disease. Now let's take another example. Let's say the fruit example. Let's say every fruit I have some features, right? Like maybe the shape, the taste, the color. I have like different sets of features for the fruits. So now I'll plot all the fruits here. All these are my different fruits. I plot them in this n-dimensional space. And now I'll only tell that, hey, there are 5 fruits here. So please, I know this data is coming from 5 fruits, but I don't know which fruit belongs to what. Hey machine, can you actually cluster them into 5 groups? So the machine, that is what the K-means algorithm. Mean stands for the mean of the cluster, which is the center of the cluster. K is the input from the user. So the user will tell you there are 5 classes or 2 classes or 3 classes. So that's what K stands for. So K-means algorithm means find me 2 clusters, mean being the center of the cluster, center of that particular data. And here in this case, it will try to divide it into 5 different chunks. So the way it actually comes with this is the algorithm. It's pretty simple algorithm. I'll go through that algorithm, but I want you to understand first like the difference between unsupervised learning and supervised learning. In unsupervised learning, you don't know where each data, we don't know whether the observation has a label or not. In this case, I don't know whether this is coming from apple or orange or grape, or I only know that this is how the data looks, and I know there are 5 categories. So I will tell the machine, now divide this data into 5 groups. So machine somehow smartly divides the data into 5 groups. We'll see how the machine does that. But once it actually divides this, so this data is provided for training, right? So this is the data I'm telling, hey machine, classify this. So how do you test now? So now I have like new data where I want to test this particular algorithm. So what it does is when the test observation comes, it plots the test observation in this space. Let's say this is the test observation. And then it will say, hey, which is this test observation close to? Which mean or which centroid is it close to? If it is closest to this centroid, it will say, hey, this belongs to class 1. Because I learned that this is class 1. If it is close to this one, it will say it belongs to class 2. Is that clear? So in the training, it will create the clusters. When it creates cluster or group is the same thing. So it'll create one group here, one group here. It'll know what the mean of that group is. Mean is the centroid of that group. It'll know what the centroid of this group is. So now the training is done with these particular values. So in this case, the machine is not, it's kind of learning a machine boundary, which is basically this, right? This is the decision boundary in this case. But now when the test data comes, you don't need all this anymore. You don't need this inside data anymore. All you need is the centroid information. So the centroid of this cluster is what it'll remember. And the centroid of this cluster is what it'll remember. When a new test data comes in, it puts it into this space and sees which is it closest to. Is it closest to this one? Is it closest to this one? So if it finds that it is closest to this one, it will say that, hey, this one has disease and this one does not have disease. Any questions so far? So I'll come across, like I'll show you how that we'll do a lot of visualizations to understand this algorithm and stuff like that. But this is the basic premise of K-means algorithm. Firstly, K-means is an unsupervised algorithm. Why is it unsupervised? It's because the data which we are giving, we are not telling what the data is. Each point, we are not saying whether it has a disease or doesn't have the disease. All we are saying is, hey, this is the data, and somehow there are two classes, right? And then the machine will actually group them into two classes and it will learn their centroids. Now, when you finish the training, now you want to test whether this machine is predicting it properly or not. When you put the test data, it will see which is closest to which centroid. And if it's closest to one of the centroids, then it will say that it belongs to class 1, or else it will say it belongs to class 2. Is that thing clear? Questions? Any questions so far?
It's clear.
Okay.
Yeah.
So this is the basis of unsupervised learning clustering. But there is still something here which we are still providing to the machine. What is it that we are still providing to the machine? I'm just giving the data, but I'm providing something else, right? What is that I'm providing? This algorithm still needs an input. What is that input? Apart from data?
The number of classes.
Exactly. So this K is still what the user provides. But in a lot of cases, what we'll see, so we will see in the future, like you don't know the number of classes. So in general, right, I'll give you fruits data. Now I'll give you, let's say, hey, this is the fruits data, and I won't tell how many fruits are there. So then how do we deal with such problems? So there is a method which I'm going to discuss. It is basically going to figure out the number of classes automatically for you. But before we go into that, let us just look at some theory behind this algorithm. But everyone understood what, like, firstly, what supervised and unsupervised is, and what is a classification problem, what is a prediction problem, and why this is basically K-means comes under unsupervised classification problem. So what K-means does, it's classifying the data into like having the disease or which class it belongs to, but it doesn't know anything about like what each of the observation, whether it has the disease or doesn't have the disease. So it's completely unsupervised. It doesn't know what the data is. So let me now, at this particular point of time, I want to just show you what was this. So we have seen how this thing works, right? So at this particular point of time, I think I want to do some basic math, because all this belongs is on the distance functions, right? So basically in Kmeans also we are dealing with something called as distance. So because it's the distance from the centroid which will tell you what that particular or how that observation is. It's how, like, how far it's from the centroid. So what are different kinds of distance functions we have? So there, it's not a simple thing. So generally how do you calculate distance between 2 points? Let's say we have a point x1 y1 and x2 y2. So how do we calculate the distance?
Square root of x2 minus x1 plus
y2 minus 1. But this is not the only distance. It's called Euclidean distance. This type of distance is called Euclidean distance. So this is only valid for points where you are actually considering the Euclidean space and then you're trying to find the distance. So let's say if I tell you, like, okay, look at this example. I give you two words. I say cat and bat. And then I give you another word, another set, which is cat and dog. Would you say that, so which of these two things are closer to each other? I give you one word, which is cat, and cat and bat is one set. Cat and dog is another set. So just from looking at the words, which two words are closer? Cat and dog is closer, or cat and bat is closer?
Cat and dog.
Just, I mean, don't get into like the category of animals and stuff.
Okay, then the first.
Just the word. So I have cat and bat and cat and dog. So generally, because cat and bat both have two letters in common, right? 80. So if you look at the words, cat and bat seem closer than cat and dog. Now in this case, you cannot apply Euclidean distance, right? So because there's no square root of, what will you take the square root of? So that kind of brings up another kind of the different kinds of distances. We'll just look at that in this next slide. So the first kind of distance, so in general, why distance, right? In general, one believes that if two measurements of objects are similar, they have some properties. For example, there are two houses. One has 3 bedrooms, 3 bath, and some square. If two, like, two bedrooms which have the same kind of square foot and, like, same number of bedrooms and bathrooms, they'll be priced closer, right? Because they're kind of similar kind of houses. So in data science observation, we saw that it can be mapped to a point in an n-dimensional space. So we can find out the distance between these points to get similar outcomes. Generally, what we see is whenever we have these observations closer, they tend to be similar. Like if, for example, I have a house which has bedrooms, bathrooms, and square foot as their features. If you plot two houses which have similar bedrooms, bathrooms, and square foot in a 3-dimensional space, you will generally see that the pricing on like Redfin or Zillow or something are similar. Like when you go to Zillow, you look at, like, they'll say that similar houses. How do they know these are similar? What it means is basically when you take these features of these houses and plot it in that n-dimensional plane, you will see that the distance between these 2 points in that space is very close. Whenever the distance is closer, we'll say that these two observations are very similar. So that's why distance functions become very important. Is that clear? So all this maps to the distance function, but what kind of distance is something we'll learn now. So what you said, x1 minus x2 whole square, y1 minus y2 whole square, is basically a Euclidean distance. That's not because Euclidean distance can explain distance between points, right, which have x1, y1 square. But then when I give you words, okay, one other example I'll give you. How many of you, like, So I'll give you an example from Seattle. Like if you're in California, then I don't know the street names and this thing. But if you're in Seattle, let's say if you drive from Kirkland to Bellevue, right? So there are how you can actually drive. You can take the freeway or you can take the internal route. So which one is closer? I don't know if you guys know how many of you know Kirkland and Bellevue in Washington? So is it closer if you take the freeway? Is it closer if you take the internal route?
Internal, right?
So actually, so internal route is basically closer, definitely. But when you actually drive on the freeway, you actually drive faster, right? So you reach Bellevue faster. So in this case, when I'm actually trying to optimize, let's say I'm working for Uber, right? And I want to come up with the estimated time of arrival. Or I'm like, let's say you're working for Google Maps, right? And you say, I'm in Kirkland. I want to go to like Bellevue the fastest way. So though it knows that the internal route is closer by purely taking the distance, but it'll still route you to the freeway because freeway has higher speed limit. So in this case, is it so you see that there are different distances which we need to use for our problem. You can't just simply take Euclidean distance every single time. So there is a different kind of distance which you need to look at here. So that's why we need to study these distance functions. Basically, these distance functions are the ones which tell us like what kind of, like in case of Google Maps, like what kind of routes do we need to take for optimizing the distance? What kind of, in case of like, in case of like word similarity. So how, like whenever you type some words, right? Okay, let me ask you this. How many of you have typed a wrong spelling in Google and Google said, hey, do you mean this? It happens a lot, right? Let's
Yeah.
say I go and type like cricket or something. Oh, sorry. 1 second. So just give me a second. I'm back. I didn't charge the phone. But whenever you're typing in Google, whenever you type a word which is misspelled, so how does Google know like what is the correct spelling? So let's say you wanted to type, let's say you wanted to buy camera. For some reason so you were saying something, Deepika?
So does it find the distance and then probably map it to a similar mean or something, like closest to me?
Exactly. So what it does is it tries to take the distance between words. And then when you type a word, it'll say that, hey, what is the word which is closest to this particular word in some space? But in that case, you cannot use Euclidean distance. You have to use some other distance. So that's the reason why distance functions need not always be Euclidean. It's not like x1 minus x2 whole square, y1 minus y2 whole square. It basically, distance functions are the different kinds of distance functions. We'll just see that. So, but anyway, do you understand the importance of learning these distance functions? It is very important because even like when you search for one word instead of the other, that's one way you can do. Other kind of distance functions are basically when, like as I said, right, while driving, if the algorithm only knows that, hey, this is the shortest distance, but it will not recommend that because it's basically dependent on time. So let's look at some distance functions which are there in machine learning. When we consider the points in an n-dimensional space, we always think the distance is Euclidean distance. But Euclidean distance is not the only distance. There are many distance measures that need to be considered for different problems. For example, there's something called as Levenshtein's distance. Levenshtein's distance is a string metric for measuring the difference between two sequences. The Levenshtein's distance between two words is the minimum number of single character edits which require to change from one distance to the other. So in this case, the distance is different. So what he says is the distance is between two words is the number of edits you need to do from one word to the other. Like for example, you have Saturday, right? So in Saturday, so what is the edit? Insertion, substitution, and deletion. Each of this thing is considered one distance. So I have A. So I have to delete A. I have to delete T, right? So because SUNDAY, and I have to actually convert R to N. Is that thing clear? That's why the distance is 3. So Levenshtein's distance says that when you have one word, in order to get to the next word, what are the number of deletions, replacements, or additions I need to do to these two words to get to the next word? So in Saturday, if I delete A, if I delete T, and I turn R into N, so there are 2 deletes and 1 substitution, I get Sunday, right? Did you follow? Why is the Levenshtein distance between Saturday and Sunday 3?
Yes, sir.
Okay. So basically, so this is one kind of a distance between these two words. So it is used for retrieving objects when user usually misspells in the word search. So this distance is what Google and they use for finding, like, so if from Saturday to Sunday there are 3, but then if you have like Monday to Sunday, right, it is only 2 because MON, you have to change M and O. So it gives you a metric how close these words are with each other, because you cannot have Euclidean distance always. Since we are going to program distance functions, let's see all these distance functions should return one single number. Like when you're taking Euclidean distance, it will return one single number. When you're taking some other distances, it will return some other number. So now let's go back to the simple Euclidean distance is between 2 points is calculated as square root of x1 minus x2 whole square plus y1 minus y2 whole square, right? Now this can be similarly extended to n dimensions. So Euclidean distance between n dimensional planes is x1 minus x2 whole square, y1 minus y2 whole square plus, x11. It's like in n dimensional plane, you subtract each dimension and you take the square root of this of the squared distances. So n dimensional plane, everyone knows, right, what the Euclidean distance is. You just have to run over each dimension and you'll get the same thing. So that's the Euclidean distance in general. But then, so there is something called as Manhattan distance. So Manhattan distance is this is also called a city block or taxi distance. So Manhattan distance is simply the sum of absolute values of x1 and y1 squared. So what Manhattan distance does is it uses this thing. So if you take a grid, right, it will tell you, like, instead of taking the square root, it will just tell you like what is the absolute value between both of them. So let me show you that in an example. So let's say you have your house here. This is your house. This is the road. So there's one more road which is like this. There's another road which is like this. There's another road which is like this. So this is another house. So what Manhattan distance tells you is the number of single times you have to cross. 1, 2, 3, 4, 5. So if you take like 2, if you put this in the coordinate geometry, if this is like 2, 2, and this is at like 3, 3. So in general, the distance between both of them is 3 minus 2 squared plus 3 minus 2 squared, right? So Manhattan distance tells you that just take 3 minus 2, absolute value of that, plus 3 minus 2, absolute value of that. This is 1 plus 1, it is 2. The reason they use this in law, in like traffic calculations and stuff. So it basically just counts the number of streets you're away instead of counting this route, because This doesn't make sense, right? Because if you have this, can the taxi go from here to here directly? It can't, because there is no there's no road which connects these two things like this. So the actual way you actually go from this house to this house is by traveling this. So is that clear why we have different distances and why do we need to learn about, in different sets of problems we use different kinds of distances. In this case we actually go from, like, yes, sure, absolutely, the Euclidean distance is like the closest between these two, but then your car or taxi cannot go between these 2 points. You basically have to go from the road, from this road to this road to this road to this road. That's why you have something called as this Manhattan distance. Manhattan distance is basically going to, it's basically going to tell you like the absolute value between these two different distance functions. Is that thing clear? So we saw one distance, which is Manhattan distance. Another distance which we saw is the, what is that? Levenstein's distance. Levenstein's distance between two words. It's generally used for distance between two words. And then there's something called as the Minskovy distance. Instead of, so basically, what is the difference between like Manhattan distance and Euclidean distance? So Manhattan distance just subtracts two of them in with like the power of 1, right? There's no squared. In Euclidean distance, you actually do the squared and then you take the square root. What this guy Minskovy did is basically he takes, he subtracts both of them, raises to a power of p, and then takes 1 by p root of that. So when p is 2, it becomes Euclidean distance. So there's a scientist who actually came up with this particular. Anyway, this is, I just wanted to give you like the different distances which we will use for calculating this thing. So there's something that's called as cosine similarity or cosine distance. If you take two vectors, the way cosine similarity is defined as cos theta between both of them divided the dot product of them divided by magnitude of both. So we will cover Mahalanobis distance when we do like covariance and correlation of the matrix. But so these are the different kinds of distance functions. So when you're doing k-means, you can do k-means by using different kinds of distances. For the simplicity case, what we will do is we will use k-means on Euclidean distance right now. But I wanted to tell you that there are other distances also where you can use for distance between words. You can use it for distance between like a distance between two houses. It's not always the Euclidean distance. Distance between two houses, basically the route you travel through the road. You use Manhattan distance for that. Is this clear so far?
Yes, sir.
So now let us look at what the K-means algorithm does. So K-means works on distance. So let me just show you some theory on how the K-means does, and then we will do some practical examples how K-means is used to determine. All right, K-means clustering. It's part of unsupervised learning. Is this thing clear why it is unsupervised? Because the data which we provide to the algorithm doesn't have labels. So we provide all the data to the algorithm, and then the machine will itself cluster it into two groups. So that's why it's called unsupervised, because we are not telling the machine what the label of each observation is. So machine doesn't know. You just give the data and tell the machine, hey machine, figure it out yourself. So in this case, I'm telling you that there are two classes here. So do some clustering method and divide this data into two groups. The reason we do that is because once we have this data into two groups, then when we want to test the data, we will see which group it is closest to. If it is closest to the first group, we'll say it is belong to first group. If it is closest to the second group, we say it will belong to second group. So let's see what unsupervised learning is all about. In supervised learning, one is given the data set and the class to which it belongs to, right? Because we have an observation and then we say it belongs to either class 1 or class 2. The aim is to correctly identify the class of a given new data set, which is the test data set. And once you train the machine, ultimately our goal is what? Once the machine learns these centroids or it learns the decision boundary, it's to test it on a new data set which the machine has not seen or which we want to test it on, right? So the aim is to correctly identify the class given the new data. In unsupervised learning, only the data is given and the algorithm needs to classify it based on the intrinsic patterns in the data. This is like the point I've been trying to tell for the last half an hour, I think. So I'll repeat that. In unsupervised learning, only the data is given and the algorithm needs to classify based on the intrinsic patterns. Like if it has two groups, it has to classify it into two groups. Supervised learning requires a lot of a priori work, like labeling for each sample, which is very time consuming, right? So when I have 1,000 images, someone needs to sit and tell, hey, this is a cat, this is dog, this is car, this is this thing. But in unsupervised learning, most cases you won't find that. So when the data is streaming, it may not be possible to label the data. So especially when you want to make decisions online, right? When you have let's say you have a data stream coming from PySpark and you want to cluster it into two groups, and then each or one practical problem about this is someone in Windows, no, not Windows. Someone basically wanted to classify, the call centers, right? Call center data. A lot of companies actually pay a lot of money to call centers because they actually, look at the ticket and then they talk to the customer and then figure out whether the ticket is actionable or not. So in one of this company, I think T-Mobile was the company. It wanted to implement. They have all the data from the call centers, and then they wanted to implement. So they knew that most call centers problems were like 5 problems. So either some of them said the network wasn't good, some of them had a problem about billing, some of them had problem about either the where the call drops or something. So they had like 5 categories, and then they used to spend so much money for call center employees to tell which category the problem belongs to. So what they did is a massive. So they got all this data, and then they said, "Hey, I'll just feed it into Kmeans, and I know it's 5 classes, right? So we'll pick features, and then we will force the machine to choose 5 classes." So then all the data was clustered into 5 classes. So next time when someone called, they just extract what all features he was asking, and then they put the problem into one of these categories. So they avoided a whole call center network and just used machine learning to replace it. So because in that case, you basically don't know. So you don't know what each category is, but you know that there are 5 categories. So you just put the data and find these 5 clusters. So in these circumstances, one can start unsupervised learning and then refine it in the future. So clustering is one of the most popular unsupervised learning technique. So based on some distance function, so we will use Euclidean distance, but if you can use k-means on words also. If you take Levenstein distance, you can use it on words as well. So when k clusters are formed, so when we will say that you usually group it into k clusters, right? That's why the k means. When k clusters are formed from the nearest mean of the class, it is called k-means clustering. So basically, k is what you provide. Mean is the center of that particular cluster. So we didn't do k nearest neighbor. We'll do k nearest neighbor KNN approach. It's a supervised learning. We'll do that in the next class. But k-means clustering aims to partition n observations into k clusters, in which each observation belongs to a cluster with the nearest mean serving as a prototype for that cluster. Any questions so far? Like everyone understands what k-means clustering is? Like why do we need to provide the number of clusters? What is the feature set which we need to take and stuff?
Yeah.
Okay. So Raghav, any questions? They must have stepped out. It's very easy to find like maybe people aren't there. Okay, so let's see how the K-means algorithm actually is used, right? So let's say we have this data. It's basically something called as Lloyd's algorithm. So in Lloyd's algorithm, what happens is that initially we take, so we have the data. We will say we will randomly pick K points as the centroids. So basically we took the whole cluster and I want to divide it into K clusters, right? So step number one, we'll pick K points as centroids. So now what we will do is we'll assign each observation to that particular cluster whose mean is the least square distance between them. So what this is basically doing is, let me show this to you like this. So the way the machine calculates this is, so you have these clusters, right? Let me just take two clusters for now. So what we'll do is initially we'll pick randomly this and this point. We'll say these are the two means. So this is randomly picked. Then what we do is we will say whatever is closest to this, we'll put it in the cluster one. Whatever is closest to this, we'll put in cluster two. So all these points will come under cluster one because it's closest to this. And all these points come under cluster two because it's closest to this thing, right? Because I put these two as the centroids. Now what I'll do is, once I have this cluster, I'll calculate the new mean of this cluster. So the new mean of this cluster, it will not be this, right? Because the majority of the points are here. So it will move somewhere to here. So this will no longer be, this will no longer be the centroid. Because after I got these things, I'll create a new mean for this particular thing. So the new mean becomes this, and I'll calculate the new mean of this thing. The new mean of this thing can still be that, or maybe it will move to this. And once I get the new mean, again, I'll redo the same thing. Again, I'll calculate the distances of every point to this cluster. And then I'll regroup that particular thing. So as you can see, like whenever I do that, so now since the mean moved here, maybe like this chunk will come into this cluster. And maybe like a smaller chunk will come into this cluster. When I repeat that, ultimately it will narrow down to this particular thing as the mean and this particular thing as the mean. So if you do that a lot of times, then the algorithm will converge into like two groups. Is that clear? So step one, like the algorithm will start with like two random points. Like it can pick any random point, 1 point here, 1 point here. It will take the distance of the points from that particular from that particular centroid, and then it will divide the data into two groups. Once it divides it, again recomputes the centroid of that group. Once it recomputes the centroid, then it will again do the same thing. So if you keep on iterating it for enough number of times, it will converge into two centroids, one with this and other with this. Any questions on this?
Can you just repeat what you said?
Yeah, so let me do that. So the way the machine actually finds this, so it's called a Lloyd's. So what it does is, maybe I should draw it, or let me see if there is a, I think I thought I had a GIF in there. So let me draw it again. So how the machine actually finds these clusters, right? So clear, all right. So let's say we have two clusters. One is here. Or let me just take a simple, let me take like 5 points. I maybe it'll become clear with 5 points. So let's say we have 1, 2, 3, 4, 5. So if I actually, like intuitively, if I tell you to say make two groups out of this, you'll generally make this as one group and this as second group, right? Based on the distance. Like if you were to group it, this is how it would be, right? Like if you were to group it, like because these three are closer, these two are farther away.
Yeah.
But if at all, now how does the algorithm figure out these groups? So what it'll do first is it'll say, I randomly pick 2 points. Let's say we pick randomly 2 points. Let's say I pick this point, and let's say I pick this point. Now I'll say, okay, these two are the centroids. Now let me calculate the distance of all the points from this centroid. So let's say I calculate this distance, and then I calculate this distance. So for some reason, like this is close, or maybe okay, in this case, all the 3 points are closest to this centroid, right? So once we calculate what like, if you look at this, now from these 2 points, it'll calculate all the distances from all these points. So let's take this point. This is the distance, and then this is the distance, which is closer. So let's say this is 1, this is 2. Is it closer to 1 or is it closer to 2?
2, right?
2. So then it will say that, hey, this is 2. Then we'll do the same exercise for this also. This is also closer to 2, right? So this will be 2. This will be 2. So now, so this is the first step, first time you iterate. So now what it will do is, now all the points, now all the points are actually closest to 2. So it will now say, this is one cluster, all this is another cluster. So after it does this, it will again calculate the centroid of this cluster. So now when you calculate the centroid of this cluster, when you do like the mean of this, the mean will lie somewhere here, right? Like if you just take the average of these points, the mean shifts from this point to this point.
Yeah.
And for this, the mean will still be here. Now it'll again redo the same thing as what it has done before. So now this becomes the second point. This will no longer be the point. The new mean will be the second point. So this is 2. So now it will again compute these distances. So now let's say 1. So this is the first point. This is the second point, because this is the mean of the second cluster. Now this is closer to this, or this is closer to 1?
1.
It's closer to 1. So now this will say this is 1. Is this closer to 1 or is it closer to 2?
1.
1. So now this will also become 1. But these two will be closer to 2, right?
Yeah.
So now look at what the new, now look at the new clusters. The new clusters will be 1, 1, 1. So these three are 1. These two will be 1. Because now it has calculated it with the new mean. But after I compute the new mean of these two, it will lie here. The new mean of this, it will lie here. No matter how many times I do this, it will still give me the same two clusters, because these three are closest to this mean, these three are closest to this mean. So in every iteration, the mean moves away to where that cluster is. So is that clear? Like how it is iterating?
Yeah.
Deepika?
Yes, this is clear.
Yeah. So what it does, it randomly assigns 2 points, and then it takes the mean of that particular cluster. When it takes the mean, it will obviously move the mean somewhere closer to this thing. And the mean of this will move somewhere here. So it keeps on doing that till it comes to a point of convergence. So once it determines these two are one cluster and these three are one cluster, no matter how many times you take the new mean, it will still give you the same cluster. So then it will stop saying, hey, I converged here. So now this is one cluster, this is another cluster. No matter how many times I choose, I always get the centroids or the means as this point and this point in the air. Mind you, the centroid need not be actually one of the observation. It can be any point. It's just a mean of that cluster. So it's a pretty relatively simple algorithm. So what it does is basically just uses this Lloyd algorithm and reiterates every single time and finds the and then finds the centroids.
So basically, it stops when
It
the
doesn't
last
find.
converge point and the this converge point this time is the same, is it?
Exactly.
Okay.
So if you look at the algorithm, it takes k randomly generated centroids. Assignment step. Each observation, assign each observation to the cluster whose mean has the least square distance from Euclidean distance from this particular centroid. Update. When you update it, calculate the new means of these centroids of the observations in the new cluster. You repeat and update the assignment when this no longer there is any change. So in our case, we just saw that when we uh, when it determines those two clusters, there is no change. Next time it tries to compute, it's the same points, right? So the centroid doesn't move. So as soon as it knows that, hey, the previous iteration and this iteration, the centroid doesn't move, then you are done. So that's how the algorithm works. Is that clear?
Yeah, this is clear.
Yeah. So, but then remember, there is still, I said, there is some caveat to this particular algorithm. Once you actually have the data, it still requires you to tell how many clusters you have to create. It won't like, that is still supervised, right? Somewhere you're telling, so unsupervised means what? Unsupervised means the machine will learn itself. When you give the machine the data, it will figure out how to make these things. But there is still this factor where you are still saying like, hey, divide it into 2 clusters, divide it into 3 clusters or something like that, right? So how do you avoid that? So there is something called as an elbow method. This is like really important and very useful. So the elbow method is actually used to determine the clusters automatically. So given the data, the elbow method will tell you what is the best number of clusters you can have in this particular data. So what the elbow method does is it just does a random search. So what it will do is it will basically create, so for each cluster, it will create something called as a distortion. Distortion is the, uh, so this is the method it does. So when you take k means, it basically takes the square root error of each of the means. So all the distances of the points from that particular centroids is basically called a distortion. So as you increase the number of k, you will find a graph which is like this. The best, I think this I will show you with an example now. Just to understand like how we find the optimal k. Elbow method says that when you plot distortion with, you just do a random search of this case. You do it for 2, 3, 4, so on up to 14. And then see whichever point is the farthest away from this line. So you basically draw a line between the first point and the last point. And the point which is farthest away from that is what? 3, right? If I join a line like this, the line which is the point which is farthest away from this line is this point here, 3. That's why it's called the elbow method. If you consider this as a hand, this is basically your arm, and this is your hand, is your, the hand, right? This is the elbow of your hand. So generally, what they say is wherever this shift happens, you see a drastic shift, right, from this to this. The point where the shift happens is the optimal k. So let me show you this with an example. It'll be more clear. So I'll show you how to write this algorithm using sklearn and stuff. But let me open up Kmeans. So but do you understand what the problem is, right? Sometimes it's very difficult to find what the optimal k is, because you are saying to the machine that, hey, k is 2, then it is doing 2. But so this is one example I have. I send this example to all of you. It's 3 clusters. So let me show you how this is done. So in 3 clusters, so if you look at the data in this in 3 cluster example, let me run it. I'll show you how the data is. but okay. So this is how the data is. It's basically two-dimensional data. You see, there are intuitively you can. I mean, purposefully, I put these three clusters farther from each other so that machine will try to find out what the clusters are. So I have some data here, some data here. All of them is in the CSV file. So now what I'll do is I'll try to purposefully force the machine to create clusters. So here I'm saying, hey, machine, create one cluster. In one cluster, all the data belongs to that cluster, right? If there's only one cluster, then there is no segregation. Is that correct? Like if there's only one cluster. So then I plot it I tell the machine, hey, machine, create two clusters. So what it did, it put these two into one cluster and this is another cluster. Then I said, hey, create three clusters. Then it'll do like three centroids where this is there. But I don't know that this is optimal. So what I'll do is I'll go and say, machine, no, make four clusters. So now machine will forcefully divide this into two of them. So if you're telling the machine, it has four clusters. So machine doesn't know like when to stop, right? Because you're telling, hey, make four clusters, it make four clusters. I said, machine, make five clusters. So it made five clusters. 6. Then like I went up to 14, but I only showed you 6. But then what I'll do is I'll plot for every of this cluster, I'll plot something called as distortion. In distortion, you can see that. So when it is 1, distortion was high. 2, it is this thing. 3, it fell really low. And from 4, 5, 6, it is actually good. So distortion is nothing but the distance of all the square root of the distance of all the points from that particular cluster. So when I plot the distortions, it actually comes up with a graph like this. And in this graph, what is the elbow? Elbow is the point which is basically considered farthest from, if I draw a line between these two, right? 4 and 14, I'm drawing a line. The point which is farthest from this line is what? This one, right? Is this clear? Like, why is this point the farthest? Or maybe
Yeah, it's clear.
So I'm just drawing a line between 4 and 14. So it's going to be like this line. So from that point, which of the points is the farthest? Like if you look at it, 3 is the farthest from it. So then I'll say the optimal number of clusters is basically 3. So this actually solves the problem of not knowing the number of classes you have. So what we do is we start off with one cluster. But is the clustering clear? Like I first give you this data and then I'll tell the machine, hey, I don't know the number of classes. Just do it for 1 to 14. So I do 1, 2, 3, 4, 5. So it'll keep on creating these classes forcefully. And ultimately it'll tell me, like the algorithm will tell me like what is the optimal number of clusters it has to print. So in the optimal number of clusters, it will tell you like 3 is the number of clusters and these are the centroids. And once the machine learns this particular centroids, next time when you give it another test data, it will see which of the centroid it is closest to. And then it will tell you that it belongs to that class. Is that clear?
Yes, sir.
Okay. So that actually mostly concludes what Kmeans actually does. So basically, pros and cons of Kmeans. So pros is basically it is fast, easier to understand. It gives us the best results when the data is well separated from each other. So this is an important point. The data is not separated, you can use K-means, but you won't get good results because if they're all cluttered together, then there is no point in using K-means, right? Because even if you force the algorithm to create two classes, it'll create two classes for you, but it'll never, but it won't be used well. You won't know that well. But what are the cons? The learning algorithm requires you to specify the number of clusters. If you don't specify the number of clusters, you can always use this elbow method to tell you what the best clusters are. If there are two highly overlapping data, K-means will not be able to resolve between those two clusters. This point should be clear, right? Because if there are two overlapping data, then K-means will not be able to differentiate between both the clusters. the algorithm converges only sometimes to local minima. Remember, I told you that it will stop at the step where it doesn't find new centroids. So sometimes when it actually hits a local minima also, it can stop. Like sometimes you need to like push through. That's why you need to use like the elbow method always to determine what is the best number of points for you to do that. K-means cannot be applied for categorical data. So that means that you cannot, you have to have it as a number, right? The categorical data meaning if you have like male and female, you have like something which is not an object, then you cannot apply K-means algorithm to that. Unable to handle noisy data and outliers, an algorithm fails for nonlinear sets. These are the pros and cons of like the K-means algorithm. We will compare K-means and PCA when I talk about PCA. But now I think so to recap, right? K-means is an unsupervised algorithm. It tells the way the machine learns the classes is by looking at the number of groups the algorithm has or the data is, and it forcefully creates clusters into those many number of groups. So the way we actually write this particular thing, now let's do a small code. So let's start with this. Let's start with the three cluster example. So I just showed you, and before we run it, I'll just show you so that you like understand K-means much better, right? Like I actually just showed it to you right now. So if you look at this, what I'm doing in this particular program is I'm purposefully creating 14 clusters. The reason I'm creating 14 clusters is because I want to come up with this elbow point. I'm kind of like cheating because I know that there are three of them, but I want the algorithm to figure out what those three are. So I purposefully create 14 clusters and then I create distortions. And if I plot this particular point in distortions, you will see that this particular point is farthest away from that particular line. So it'll tell you like 3 is the best number of clusters for it. And you can see how the data is being clustered also. If it's one cluster, it just puts everything into one. If it's second cluster, it puts this one into one and these two become one cluster. 3, it perfectly divides the data into 3 clusters. And then you can say 4, 5, 6, 7, and you will see that it divides it further into subblocks. So there are two files which actually I wrote for this before you start coding. I wanted to show you the other thing. The other thing I have here is accelerometer data. So the accelerometer data, if you look at it like that, I sent you these 3 files today. So one is the 3 cluster example. That is what I showed right now. And if you look at the accelerometer data, it actually contains 7 classes. So you see, the accelerometer is something which is used in all the hardware devices. It actually has an X, Y, and Z location. Let me just show you this. It has X, Y, and Z location, and this I purposefully put the class here. So this belongs to one category. There's like a lot of data, and then you'll see that there are 7 classes. So you see there are 7 of them here. So I wanted you to figure out like how the elbow method to tell me that there are 7 classes in this. So I think the goal is clear, right? So there are 7 classes. I'm telling you prior, but then you have to use the elbow method to figure out that 7 is the optimal one. So I written the program for that also. So Kmeans accelerometer. When you run this, so it'll predict that 7 is the best number of classes, and it'll show you how. I'll talk about confusion matrix in a bit, but let's start with programming this. So what do we need to program K-means? So firstly, there are 2 libraries which we need to import. One is called sklearn and other is called Skippy. So create a new project. So file, new process, like new project, and create a new project called Kmeans and add it to the same directory. Kmeans. If you create it, it'll tell you open in a new file or create a new one. So you basically add it to the same project directory. So you add it to that directory and add. So you need like 4 packages for this particular algorithm. So the 4 packages are sklearn, pandas, numpy, and matplotlib. So if you are writing the code, create this thing and create these 4 packages. So if you go to Kmeans, the packages I have is pandas, numpy, matplotlib, and sklearn. Are you guys creating the project?
Yeah.
But overall, like, so do you like? I mean, what do you feel about like K-means algorithm in general? Like, it's really cool, right? It can predict how many number of clusters it has. It can tell you like in a data when you don't have any classes and stuff, you can easily like come up with how many classes it is supposed to have and stuff like that. So it's very useful when you want to do like unsupervised learning. So there's one more level of learning. It's called hierarchical clustering. So we'll cover it once if we have time. That's another method of unsupervised learning. It's called hierarchical clustering. But K-means as such is the starting step for unsupervised learning. So let me know once you're done. So 4 packages: numpy, pandas, matplotlib, and sklearn. And sklearn is like the standard library which we will use to learn like other algorithms also. There's one thing I wanted to actually tell you, like there are a couple of ways you can import libraries. You can either import the whole library, say import pandas as PD, or you can import only a certain section of that. So you can, like for example, in this particular library, the way I imported it is called from sklearn.cluster. I imported only Kmeans. So because sklearn has like a lot of libraries within it. So there's Kmeans library, there is SVM, there is like a lot of other things too. So this is the other way of actually importing it. Forget about the elbow point for now, but let me just walk you through the code. So elbow point is something I had written, what I told you, right? Like I found out the square root of distances from those points. And then I created a graph with the distance, and I created what that array should be. I'll send you this particular function, but it's very simple to actually call k-means. What you do is, again, you use pandas data frame, and you actually read the data frame into your data this thing, and then get the data out. The data comes from df.values. So in your data frame, when you read from accelerometer, you will actually get all the values of that data frame into data. And all you need to do is say predictions. We have to create like, sorry. So you have imported this k-means library, right, from sklearn cluster. So all you need to do is just pass in that. So the code is just this much, 5 lines. You have to pass in k-means and then say what is that number of clusters you create. That will create your k-means model, and then you will say that model dot fit the data. So this is basically, so your k-means model is saying I want to fit 7 clusters into this particular model, and then I pass in the data to it. And how do you know what each point is? You will just say dot predict data, you get all your points. So it's just 4 lines of code to do the whole k-means clustering. So I'll first let you create the libraries and import the libraries and read the data frame. Forget about the elbow method for now. I'll give you the code how to write the elbow method. Elbow method is pretty straight. I mean, It's basically just taking the maximum distance of the points from that particular line. But all you need to do is once you create these libraries, sklearn. Now, once you import these libraries, you have to call the library, create the Kmeans model into Kmean model, and then use dot fit data. The data comes from your data frame. df dot values is your data frame, and then you will use Kmeans dot predict. You will get the predictions of that particular. I'll wait for you guys to code this. Use this for the accelerometer data. And let me know if you have any questions. Are you guys importing the packages now? Any trouble importing the packages?
No, not as of now.
Okay. Any questions on this? Like, so once you import, you actually can just import K-means from, the sub package. So sklearn has something called as cluster. So instead of importing the whole thing, you just say from this cluster, I just want to import K-means. So you can actually, yeah, you need not import the whole thing. So generally, when we did pandas and numpy, we just did import numpy as np, right? So now what we are doing is we're just doing from this particular cluster, we import Kmeans. And then the way we use this for fitting the K-means cluster is basically uh, by fitting the model. So you basically take all the data. So in this, I only take the data. Why did I do 1 to column minus 1 is because in the accelerometer data, the last two are, the last one is the class, right? I don't want the class to be fed to the data. I just want 1, 2, 3, 4, all these 4 parameters to be fed. So so when I read the data frame, I don't take all the columns, I take all rows, but one column minus, number of columns minus 1, and I feed that to the data. And then I create a model called K-means with n clusters. And then in these n clusters, I'll actually have, I create the K-means model. I do K-means, a K-mean model dot fit, and that will fit the data. So it'll create the models, and then the predictions, what it will tell you is kmean model.predict will tell you which data is being put into which class. So the predictions will actually come as, you can see, I mean, I've actually outputted the data as prediction also. So what I did here is I put the data frame, I added something called as result, and I put predictions into that result. And I rewrote that file as accelerometer1.csv. So I did, so remember how we did the cleansing data, we converted into 2 CSV. So df.2 CSV, I actually converted it into accelerometer1.csv. And then I put it. So if you look at accelerometer1, that will have the class values. I mean, accelerometer has the original class values, but this will give you the result class value. So I added one more column called result. So you can see here that it was class 1, but it predicted. So this accelerometer data is like very jumbled. So it has like not everything is accurate. So you can compare that it was actually class 1, but it predicted it as class 4. But then most of the time it will predict it is correct. So 3 is predicted correctly, 4 is predicted correctly. So it's not like 100. That's why I did accelerometer, because it was like all jumbled, right? Sometimes you won't have clear distinctions between classes. So then I wrote all that results to accelerometer1. So the best way actually to show the results in general is by using a confusion matrix. So there's something called as a confusion matrix. So I printed out the confusion matrix. So what the confusion matrix tells you is, so if you look at this thing, so this is basically the confusion matrix. So we have like 7 classes, right? 1, 2, 3, 4, 5, 6, 7. So what the confusion matrix tells is basically the first row is all class 1, but how many of them have been predicted as class 1, how many of them predicted class 2, class 3, class 4, class 5, class 6, and class 7. So in general, and second row, basically, so row and column. Let us just talk about confusion matrix, because this is one standard way of showing the results of the data. So there are 7 classes here, right? So confusion matrix is generally used to show results. So let me do share. So generally there are 7 classes, right? 1, 2, 3, 4, 5, 6, 7. So confusion matrix is basically every class we actually, so first row, all of them belong to the first class. Second, everything belongs to second. Third, everything belongs to third. So this is the number of ones which belong to class 1, number of ones which belong to class 2, number of ones which belong to class 3, 4, 5, 6, and 7. So in the first actual, this is actual, right? This is predicted. And this is actual. In actual labels, out of like all the samples, right, which have 1, how many of them are predicted as 1? So let's say in this case 300 are predicted correctly, and even though it is 1, how many of them have been predicted as second class? That is like 200. Third class, so, and then so on. So in the second case, actual label is 2, how many are predicted as 2? So let's say in this case it's 400, there'll be 100 here, 20 here, 5 here, 8 here, 2 here. So the confusion matrix is this matrix. So if you actually see the diagonals of the matrix is the ones which are actually predicted. So class is 2 and your prediction is also 2. Class is 1 and your prediction is also 1. Class is 3 and prediction is also 1.
Yeah, imagine if it's 4, then the prediction 4 is the correct one, right?
So if it is 4, then the prediction 4 is the correct. Like
Okay.
This is the actual label, right? This is what the class is there, and this is basically the predicted label.
And then
So
everything else is predicted wrong, right?
everything else is predicted wrong. So in this case, all these are predicted wrong. Only the first one. So only the diagonal elements are the ones which are predicted correctly.
Okay.
So that's what a confusion matrix is. So generally, most of the time, they display the results as confusion matrix. So in general, when you have a multi-class problem, the way you actually display the results is by plotting this confusion matrix. So you can see that when the data is very garbled or like jumbled, so when the data is jumbled, you can see that here the first class only 510, there it's predicting like class 1, but it's predicting a lot of them as class 6. So it is not good for like class 1 prediction, but you can see that in cases of so if the data is too jumbled with each other, k-means may not work as accurately. You see the diagonal elements are not the highest, so it's always predicting something or the other. So this is an example where k-means is not a good algorithm to work. But if the data is linearly separable, or sorry, if the data is clearly distinguishable, like in case of like 3cluster.csv, right? In this, we purposefully created 3 clusters. So in this case, it will work like a charm because it actually does predict what those 3 clusters are. In this case, it actually, because the data is all jumbled up, it's not a really good mechanism to. This is how you print out the confusion matrix of a class. You say confusion matrix, and then you actually have, so you give the actual class and then you give the result of the class, and it'll, and the confusion matrix can automatically be got from the sklearn metrics library. You can import confusion matrix. Anyway, at this point, I think I'll let you guys code. I'll send both these coding examples also for you to like see and follow. But any questions so far? Anything you didn't follow or? Deepika, any questions?
No questions. So I just want to go through the code and then probably execute it on my own and then see.
Okay.
Thank you.
But you're able to follow like Python and this thing, right? So
yeah.
You just covered the basics of Python, which are required for the algorithms as such. But this is the first algorithm, so I'll let you guys figure out sometime. So why don't I do one thing? Maybe it's difficult to code it up right now. I will send you my code, both this one and the 3 cluster example. Take your time, like go through the code and see, run it, and then see if you are able to like if you have any questions or anything. So most of the I've coded up everything here. I've coded the elbow method. I've coded the how you read it, how you use k-means clustering and stuff. So like up to you guys. So should I send you the code and will you go through it at your own pace, or do you want to write something now?
I think you can just send us the code.
I'll send you the code because it's difficult to like sit and like look at this and write so far.
Like we can learn more stuff here and then apply it later.
Yeah. So these also like in case like you want to use these machine learning models for your problems in the future, right? So you can just use this as a reference on how we call the libraries and stuff like that. So there are 2 models here. The first one, k-means, this one I didn't even use the package. What I did is I I did it myself. Like I created the model, I predicted it, but then I printed out the distortions and I printed out the elbow method and I found out the optimal point and I redid this thing. So I think I'll send you this code and then let me know in the next class if you have any questions on the code. We can go through them in detail, because right now seeing this and writing it might be a little difficult because there are like a lot of things, right? So I think it will work as an assignment as well. But from a theory aspect, is everything clear? Like, why do we use k-means? When do we use k-means?
Yeah, that is kind of clear now. I just want to try the implementation part.
Yeah. So I will send this code out to you. And the only thing, so there are two files. One is the k-means, the 3-cluster example. In the 3-cluster example, I actually have the plots. So the plots will actually help you visualize like like this is already 3 and it'll help you understand how the elbow method works, and then what happens, or how do you visualize if for each cluster, if it's 0, 1, 2, 3, like how the clustering behaves. So you see, if it's actually 3, but if I tell it to do 4, it'll do 4. It'll cut this into 2 parts. So that will give you an understanding of how k-means clustering is actually working. And the second one is accelerometer. In that case, like the data is all over the place, so it doesn't work for the accelerometer case because there is no separability in the data. So okay, then I'll send the code. I'll post the recording as well. I think this is all I had for this class. So I wanted to start with one unsupervised machine learning algorithm, and next I'll start with one supervised. We'll do k-nearest neighbors in the next class, and that will give you an insight into this thing. And if time permits, I'll talk about PCA and eigenvalues and eigenvectors. So any further questions on this, or if not, then I will stop the class and I'll send you the guys the code.
No questions.
Okay, I'll send you the code right now for this, so you can take some time to make this thing. So I will. Yeah, if there's no more questions, then I'll stop the class and I'll just send you the video and the Python files.
Yes, I will go through it and then probably we'll just get back to you if we have any doubts.
Definitely. Okay, so we have a class next this Wednesday, but there's no class on next Sunday. So you can utilize the Sunday to revamp all the exercises and like go through the ones which we covered if you're lagging behind on assignments and stuff. But in general, use it as a means to learn like Python as well. So it will be helpful for you to I know we are using Python only for data science, but in general, Python is a good language to know now because it's being more and more popular as time passes. So, and one good thing about these things is it'll tell you even how to program in Python and stuff. All right, then. I'm stopping the recording.
All right. Thank you.
Thank you.
Okay.
Thanks, Sai. Thank you.
Thank you.